Okay, so in the first part of this talk, we covered a number of things. Let's remind ourselves what we talked about. Remember that the general objective was to find a parameterized mapping called T that is parameterized with theta that
Mm-hmm.
takes in samples, xi's from a simple distribution P0
Mm-hmm.
and maps them to samples on a complicated distribution. Now we want to optimize the parameters such that this dashed blue line, which is the push forward of P0, is close to our data. We started by writing a simple loss function called maximum likelihood. And we said, okay, if we have data and we can somehow quantize the closeness of p data to our generated samples, then maximum likelihood means changing the parameters such that there's a good fit between the data and the model, right? So that was the overall goal. And we quickly changed the probability or likelihood itself to log probability or log likelihood. Why? Because if the probability is close to 1, its log is close to 0. So maximizing, right? And if it's close to 0, its log is close to negative infinity. So they change in the same way. It's easier to work with log probabilities. Numerically, it's more stable. All right. The next thing that we visited was these normalizing flows. With the way where we think about them was just a series of transformations. Each transformation is simple so that we can keep track of the Jacobian of the transformation, and we would apply them like layers. We can, because they're invertible, we can go from P0 to the target, or we can come back. And we saw that we can calculate the log likelihoods, which means that we can optimize the log likelihoods. That's by changing the parameters, we can maximize the log likelihood if you like, and that's how training is done. Once the training is finished, we can drive new samples by taking one sample from P0 and passing them through these layers of normalizing flow to get a sample, hopefully on this cross-shaped target data. Okay, continuous normalizing flows. We looked at a layer of normalizing flows and it looked like something like this. Phi is x plus some function that depends on x. This is very close to a discretization of an ODE. What do I mean by that? Look, xk is xk minus 1 plus some update on xk minus 1. If you think of that in continuous case, now this is equivalent to an ODE. The ODE would start at an initialization state x0, and the update in the continuous case is actually equivalent to a velocity because you start at x0, the velocity field takes you through different states, and we have to find a function u that takes us from x0 to the target data. How do we do that, right? Um, okay, I think this is where we left off last time, so let's discuss this. It's a if we think of four as transforming samples, right? There is an equivalent theory that tells us what happens to the probability density function itself. So this number four, equation four, is telling us how samples, states like X, move through space and time. They move according to this differential equation, but the state or X is just a sample from a probability distribution. And we can think of probability distribution as, a distribution of mass. So you have a quantity mass 1, and you
Mm-hmm.
distribute it maybe in one dimension in whatever way you want. Sometimes you distribute that uniformly, so you have a mass 1 and you uniformly distribute it between 0 to 1, for example, so the entire mass is just 1. Sometimes you create a shape like this, for example, so the same mass the same integral 1, you can distribute it differently. Now, if you want to know what happens to this distribution, right? P has a distribution. What happens to that? P0, and then maybe you transform it to some other thing, P1, right? This is the equation that tells you how the distribution evolves in time. If you ask me where it comes from, let's not go through the derivation today, but I'll tell you that it comes from physics. There's something called continuity equation that basically says the amount of mass that you have is fixed. So if you integrate this, if you integrate that, the amount of mass should be preserved, right? So this equation comes from the conservation of mass. All right, take it from me, because we don't have time to derive this. Take it from me that this is the sort of tied to equation 4, and it tells us how P, the probability distribution, evolves in time, right? dp dt, the rate of change of the function, that is the distribution, in time. Well, let's look at the second term here, is related to divergence of u times p, right? Okay, divergence, I don't know if you remember from your calculus, but divergence is, in one dimension, divergence is, easy to calculate. In 2 dimensions and 3 dimensions, it goes to calculus, right? But if you remember, divergence is something that looks at a vector field, something that has directions, and it adds up the terms in it. So it's like the dx of u, if u has 2 components, u x p plus d dy of u y. Look, you can look up the definition of the divergence anytime. That doesn't matter. What I want to ask you is, does it make sense that u, the velocity, is a vector field that has 2 components, for example, ux and uy? Does this make sense? Can you imagine the velocity
in 2D? Yeah.
in 2D?
Yeah.
Right? It makes sense, right?
Yeah.
Because you can move this particle.
Mm-hmm.
Look, we write it as x0, but x0 is the zero is actually related to time zero. It doesn't say anything about how many components are there in this guy, right? X0 can be the coordinates of 2D coordinates of a sample, right? It can have x direction, y direction. So if we are moving particles that are 2-dimensional in time, well, the velocity field has 2 different directions. By what speed is this particle moving in the x direction, and by what speed is it moving in the y direction? So it shouldn't be a surprise that u is a vector valued function. It's a vector. P, on the other hand, so up looks like something that is a vector value thing multiplied by a distribution, which is a scalar function. So this entire thing is a vector, which means that you can take a divergence, right?
So in 2D dimension, the vector value of the u would have 3 dimensions, because it's not ut, it's like u. I mean, the time we have to
The time component. So
Yeah.
you can think, very good question. I like that. We can think of, so now let's think of this u as a vector valued function, right? I'm going to remove p for now. And we just said that it has 2 components, u of x and u of y. But if I look too closely, u in the direction x, right?
given time t.
Very good. Very good. Also, what other thing? What other thing? the velocity, is it the same everywhere? Not necessarily, right?
We're talking about like the specific point X right now. So,
So you can have, very good, correct.
uh,
But if you want to look at a function that tells you what is the velocity at every time point and every x point, it can have another input, and that's the x, right? Most general thing that we can consider is a vector of two things. Each one of them are a function of time and space. Like you can have zero velocity in, you know, in a specific point, and you can have maximum velocity in other points. So it needs to be a function of a space as well. That is the most general formulation. So you
yeah,
can see it, u here, u is a function of x and t. Now they're so detailed here that even x itself is a function of
the
t.
function of t.
But if it helps, right, the
Yeah,
particles move, right?
yeah.
Okay. All right. So now the divergence is something that looks like this: d dx of the first component plus d dy of the second component. That's, that's what the divergence means.
Yeah.
In one sentence, divergence is if you look at the velocity, for example, this is the velocity field, so it's pushing everything to the right. Divergence is if you draw a small circle, how much is the flow going out of it? So some particles are flowing in and some particles are flowing out. What is the net rate of particles flowing
Oh,
out?
okay.
That's why it's called divergence. Like it says, in a small area,
Mm-hmm.
are we getting net influx or are we getting net outflow?
Outflux.
So that's what it means. Okay. All right. So up to this point, we like these two equations. We like 4 and 5, which is directly related to it. Why?
Mm-hmm.
Because if, for example, you have trained a model that learns this velocity, now you can draw a sample, x0, and then integrate, somehow figure out a way to march that sample x0 through time by, correcting for these velocities, right?
Yeah.
There is a simple way of doing that. But also be like 5, because why do you think we care about this p, this distribution, and how it changes over time? What do you think about that?
Because we have to build this probability path. So,
Very good, right?
yeah.
Because we care about optimizing the model, right? So you need to somehow maximize log probabilities.
Mm-hmm.
And this equation tells us how the probabilities change over time, right?
Mm-hmm. Yeah.
You remember the overall goal is to train a model. Training a model means maximizing log probabilities.
Mm-hmm.
And I don't, I am not interested in the probability at time 0 because I know what it is. I
Mm-hmm.
designed it. You designed it to be Gaussian.
Mm-hmm.
What you're interested in is what is the probability at time 1, and this solving this equation will tell you what it is. Both of these two things are right now very time consuming and hard to do. So we will make it easier pretty soon, but that's the general idea of what we can do. So here is a summary. There's a probability path, right? So P0 and then PT takes you from P0 all the way to P1. This is done by velocity field that we need to figure out. And if you solve that, it will give us something called flow that exactly tells us where particles are going at each point in time and space. But also we can, on the other side, what we can do is we push forward the base probability. We can track not where the states or particles x's are going, but where the probability is going. So these things are linking between each other. Okay. Any questions up to this point?
No.
Okay. Very good. Very good. All right. Now, so continuous normalizing flows, right? We saw normalizing flows. Now we're going to consider continuous normalizing flows, or CNFs, right? These are a special case of this,
Uh-huh.
right? Okay. Um, let's see, where we basically keep track of how so this is if this is the equation for changing the probabilities, we're interested in log probabilities. So we take a log, right?
Mm-hmm.
And it's related to the, look, it was already related to the divergence here,
Mm-hmm. Uh-huh.
right? But by taking the log, if we do the math, we lose the PT.
Uh-huh.
So the change in log probability is directly related to negative divergence of the velocity field, right? So that way we can directly evaluate what is log probability at time one by
Mm-hmm.
integrating this and starting at the velocity at time 0 and just going forward, right? So there we go. Okay. What part of this is tunable? What part of so in normalizing flows, we had layers, and each layer had a simple mathematical formula. It was invertible, and we could tune it. Now, instead of layers there, we have a single neural network or single parameterized function. It doesn't even have to be neurals, any kind of parameterized function that you can train. And that single one is u, the velocity. So now you can already see that we are moving towards flow matching, right? You studied flow matching, and you know about, matching the velocity, the desired velocity to the velocity predicted by neural network. We are already moving towards that. And I want you to notice that we didn't have this u of theta before. We had in discrete normalizing flows, we had things that looked like this. We were dealing with transporting X or samples itself, right?
Mm-hmm. Yeah.
There was no notion of velocity field. So by moving one step ahead, we now have introduced this notion of velocity field, and we are directly approximating that velocity field using our neural network, right?
Yeah. Yeah.
Okay. Let me think about this. There is one more thing that I want to tell you. So we are not fully onto flow matching yet. The
Mm-hmm.
difference now is that um, so log probabilities, very good. The main benefits of, let's see, the continuous time, okay, inverting, something about requirement flow, I don't computer like that. Okay, yeah, I get it. But still, we need to solve ODEs, right? We need to solve ODEs to get a new sample, because we
Mm-hmm.
need to integrate this equation, and we need to integrate this equation for during training. Why? Because we want to maximize the log likelihood. This is the equation for the log likelihood, but it's a differential equation, so we need to solve that, right? So
Mm-hmm.
which means that both during the training and once it's trained and you want to infer a new sample, you need to solve these costly ODEs.
Mm-hmm.
Can we do better is the question, right? Can we do better? Okay, so conditional flow matching is an attempt to improve that. Now, the word conditional, as you have also explained, refers to the fact that as data, we only have access to samples on the initial side, on the base side, and on the final side, target side, right? But what we are going to do is we will define a velocity field that is conditioned on some variable that we create called z. And this z depends on x0 and x1, but we build it, right?
Mm-hmm.
And then we create a u
That is
of
sample
x.
this.
Very good, right? We sample this and then we build a U that depends on that
Mm-hmm.
sample's Z. Very good, right? So that's why, I mean, originally that's why it's called conditional. But you will see that if you want to get rid of this Z, we go through a process called marginalization and we can find U everywhere, regardless of what samples we draw. But it's a
Mm-hmm.
process of marginalization. In another way of saying it, it's a process of averaging. Okay,
Mm-hmm.
we will see all of that. Now, let's start here. So what do these three graphs tell us? We know that mapping one probability to another, right? There are multiple ways of doing it. You can design different pathways. We are looking for simple ones, the ones that help us during training by maybe simplifying our computations. We will see at least two of these today. Okay, so that's that for this graph. Here is an example where we learn to map a simple Gaussian to a two-component Gaussian with different means, right? That's what it means. This is the result. We know that the result of this has to be a velocity field that takes samples, and if we move the particle samples through that velocity field, according to that, it will, over time, all the different samples will give us a new distribution on this side, and this distribution has two peaks now. So this is one way that we can do it. Okay, very good. All right, this graph is basically showing us that even if the initial base final target are the same, you can have multiple probability paths. So we need to specify what kind of probability paths are we interested in. Okay. So how to define a probability path? So the first example that they give us is a simple linear
But
interpolation.
at
Yes,
the end of the day, all of these probability paths would lead us to the target distribution, right?
correct, correct. The
So
question
why?
is, the question is, what is the difference between them, right?
Yeah, why do we care about that?
Yes. Um, mm, what I think is the answer is that some of them help us in computations, meaning that
Oh,
it
oh.
simplifies the computations. But let's wait and let's keep that in mind. I have the same question. So after we see some of these, let's see if it actually makes it easier to calculate, or is there another reason, right? Maybe there's something we're missing here. Okay, so the linear interpolation, uh, as we have discussed before, takes a variable, takes a sample z,
Huh?
which is a tuple of base samples that are simple to draw and a data point, right? So from P0 and P data, we sample X0 and X1. 0 and 1 here refer to their time points. X0, it comes from P0, X1 comes from time 1, which is P probability data. Okay, good. Let's move forward. Now, we have to specify, because this is a probability pass, we have to specify what is the probability at all other points. Well, so probability of X and T, I know that it's after the conditional, but we always evaluate these things by knowing what time we are looking at. Probability of X given some specific time point and given a sample x0, x1 is by choice a normal distribution.
Of
Right.
alpha or Q.
Very, very good. Some interpolation between x1 and x0 plus some small noise. Some small noise, right? So what does that mean? Well, look, if this is our draw of x0 and this is our draw of x1, the 1 minus tx0 plus tx1 is just an interpolant that goes through this, right? But we don't want to just choose points on this line. Maybe we also want to choose points that are very close to this line. So we also give it a little bit of flexibility. So we consider a little bit of flexibility around it. So this standard deviation tells us that there is a halo, there is a margin around this line that we can sample points around that as well, right?
Yeah.
Okay. The others say that it's fine if you don't want to sample, if you want to keep it exactly on the line. And in that case, the probability pass is no longer this Gaussian. It's a Dirac delta distribution, which is just one on the line and zero everywhere else. That's fine too. That's okay too. So here are a bunch of different examples. We know that it depends on the draw of x0 and x1, so you can have different probability distributions depending on what you draw.
Yes.
But uh, let's see what happens, right? If we take this probability and marginalize over different draws. Marginalizing means that we take different z's and we average over all of them, because if I have a function of p of x and t, right, given z, right, the way that you can marginalize is you draw a lot of different samples of z and you integrate over all of them, right? But so the result of this is actually p of x, comma, t, comma, z, but we don't like z, so we integrate over all possible z's. Integrating is an averaging over however many samples of z you have. So 1 over n number of z's, right? So in this side, you will see that if as we draw more and more, we will average them, right? So
Yeah.
see what happens over time as we draw more and more, right? Here is that. So as we draw more and more and we average them, it looks like it is converging to this probability pass that in fact takes a single Gaussian and maps it to a two-component Gaussian, right? So this gives us an intuition that these probability paths over time, if we draw more and more of them, they are converging to something nice for us. All right. Okay, now, what is the velocity field that is tied to this probability path, right? Remember that conditional flow matching, we want to be able to specify simple probability paths, which means that we need to define how to draw samples away from 0 and away from 1, but also how to transport those samples. Right, so here is one second, let's see. We went too far. Um, okay. So here there is basically a conditional probability path that for a specific pair of x0, x1, this is how we will transport things, right? It might not make sense until we actually take a time derivative of this, right? Get that. Time derivative of this is what? T times x1 plus 1 minus t.
Actually, I have a question.
Sure.
We we consider t as a random variable, as it says, for like drawing the probability path, right? For
Sure.
like building this up. But
Sure.
why we randomize it? I mean, we can like why we don't like put it like time by time forever, like
I think if you step through time, it's fine, but you will only be training your model at time equal 0.01 and 0.02 and 0.03, right? So you create a long list of training points and you always train your model on these points. Whereas if you truly sample through time as well, every training point would be different. So you get access to lots of new training data by this way. Does that make sense? Right? If I only fix my time to a grid, although at this time
no.
point,
Could you go up a little bit?
sure,
Right.
let's see.
No,
Maybe
it's
this
not.
is getting,
It's not moving for me.
oh, okay. I understand. 1 second. Here. How about now?
No, no, no. The video, the loop video that we had. Uh,
Oh, okay. Okay. Here we go.
yeah,
Good.
each of these lines is it like the random time that we choose, right? Each of the line that we have, I mean,
Um,
this distributions technically.
no, they're plotting it for, so they are plotting it for all times actually for because they want to visualize it. Reminder that this axis is the time and this axis is the x. So the only thing
Okay. Got it. I got it. I got
in
it.
practice we do sample and time as well, but
Mhm.
they want to show us this line. So and this line ends at t equal on this axis ends at t equal 1, and on
Mhm.
this axis starts at t equals 0. So this direction is time,
So
this
we
direction is
random,
space.
so we randomly choose two time between 0 and 1, or
Yes. Yeah, in practice, you do that. You don't just do it like a grid of time at fixed time points. Because, right, if you do that, you train your model to work well here, sure, work well here, but what about in between? If you truly
right?
uniformly sample,
Mhm.
right, although you here, you, so
I mean,
although what you're doing, like essentially you're saying, hey, I'm here, can, and this is my x0 and this is my x1, right? Can you teach the model to move towards this direction?
mhm.
Now, next time that you're at exactly at this time point,
To not move to that. I mean, at this point, we just want to build a probability path. So we're not trying.
okay, we haven't talked about it yet. That's true. That's true. Very good. Right. So let's continue to see why that's the case. Look, if this is the, hold on, I need to go up. Okay, if this is the conditional probability, right? P
Mhm.
of x,
Mhm.
but conditioned on z, right? This is a Gaussian, and this is the mean point, and this is the error on top of it, or
Mhm.
perturbation on top of it. So this is basically where the x is going to be, because it's this is x0, this is
Mhm.
x1, And this is a random, depending on what you draw here and here, these are the different x's that you will get for different times, right? Okay.
Yeah.
So if this is the x, what is the conditional? U conditional. Conditional means only tied to this specific draw of x0 and x1. What is the conditional velocity? Well, if you remember, dx dt was u. So if you
Mhm.
have access to conditional x given
Mhm.
z, you have access to u conditional u of x given z. And
Mhm.
that's the derivative of this guy. And the derivative of this guy is pretty easy to calculate. Derivative of time derivative, right? Derivative of t times x1 is just x1.
Mhm.
No, 1 minus tx0 is minus x 0.
Mhm.
So
Yeah.
this
Yeah.
is the conditional velocity, meaning that if not not over many, many, many samples, but only for the sample that I draw here at
Mhm.
x0 and x1, the velocity field that I have to follow only for this is on this line. The
Yeah.
equation for that is just x1 minus x0, right?
Yeah. Yeah.
Okay, good. Then we are at a good place. Here is the
And
result.
then we integral all over this, and since we cannot calculate this integral, we use the neural network. But
Very good.
uh,
But then why is this useful? Can you tell me if we are going to use the neural network to approximate the velocity? Why is this useful?
uh, what you mean? I mean, we integral all over all of these points. So what I can get.
If you have a neural network, you want to train it, you have to show it some training data, right?
Hmm. Oh, yeah,
How
yeah,
do we create training
yeah, yeah,
data
yeah, yeah.
for that neural network? We
Hmm.
use this conditional
Yeah.
velocity field. Very good. Very good. Okay, excellent. So you saw this effect, right? Now I'll tell you about one more, and that's the conical Gaussian paths. They're actually very simple. They they're very similar to this, but we assume that x0 doesn't matter. Essentially, x0 can be the entire x range, right?
Hmm.
So z here, by choice, again, this is a conical Gaussian path. By choice, z is only drawn by looking at the data points and pick on the data side and only picking one.
Hmm.
But the probability path is just t times x1, the mean of it, and here the standard deviation or the variance is 1 minus t.
So we choose
Let's
another probabilistic path.
It's definitely another probability path. Here, the standard deviation of that Gaussian was fixed no matter what the time was. We always take a margin around the point, and
Hmm.
how far we go away is always determined by this variance, and it's fixed. It's
Hmm.
not time dependent. But the new choice is taking t times x1 as the mean, and the variance changes with time. It changes very smartly. As time goes to zero, I'm sorry, as time goes to one, the variance shrinks to zero, which means that this is time, right?
Hmm.
So as we get closer and closer to time one,
So
we don't sample too far away from the data. We sample exactly close to what the data is, x1 is. But when this time is close to zero, it has a wide variance, which means that we we might consider these
uh,
points, everything.
can
So
can
that's the
can
conical one.
can we try to apply the previous probability path on this problem, so we can see like if we choose. I mean, do we have the term of wrong probability path in this term? The previous one that we had for the previous problem. The
So it depends. What do you mean? Are you suggesting that we can make this variance time dependent
No,
or
I'm trying to apply the problem that we just saw with this probability.
Oh,
Not
okay, sure. So they have the simulation for it. But before doing that, it makes sense. This probability pass makes sense, right? On the time equal to 0 side, right? This is n of t is 0,
Mhm.
comma 1, right? So
Yeah.
it can be anything, right? So mean 0 and standard deviation 1. So it's a very wide thing. That's fine. And on the other side, it is an x1 comma 0. So a normal distribution with mean x1, but with no variance. So it's exactly x1.
Yeah.
Everywhere in between is on this cone, right?
Yeah.
Okay, so now this is what you wanted to see. Let me play the animation. So on top, it's the new sample. On bottom, it's the average of all samples.
No, yeah, definitely it would work, but I'm trying to say that what if we choose another probability path for, I mean,
Okay,
another
that's
probability
fine.
value?
That's fine as long as we respect the two boundaries, right? So on this boundary, it's simple to sample from,
Mm-hmm.
and on this boundary, it goes or shrinks to the data. And
Mm-hmm.
also we can figure out a conditional probability pass for it because we
So,
need conditional probability pass as reference data for the neural network,
yeah,
right?
yeah, yeah. But so we can use the previous probability path for this
Mhm.
problem.
Sure. Or you can come up with your own probability pass too. Yeah.
Mm-hmm.
Yeah,
Yeah.
as long as these, I believe there is the specifications somewhere, right? If you read this, they give you three conditions,
Mm-hmm.
at type 0, at type 1, and
Yeah,
also
yeah.
it's easy to find out what is the velocity field. So for this one, for the conical one, the velocity field is this.
Mm-hmm.
X
Yeah.
minus x1 over 1 minus t.
Mm-hmm.
Okay, yeah, so here are the general construction of conditional probability pass if you want to come up with a new one
Okay.
yourself.
Yeah.
Okay, now pretty quickly, let's transition to the unconditional velocity. And you already know that in order to go to the unconditional probability pass, we marginalize this conditional one and we get something like this. There's this question that what is the equivalent of this for velocity field, meaning that whenever I sample,
Mm-hmm.
I know where the velocity field will take me. It starts at x0 and it will take me to x1, right?
Yeah.
What happens if I marginalize over all of them? What happens if I average all of them? There is a little bit of mass here involved,
Mm-hmm.
right?
Yeah.
So inside of that is that calculation, that derivation that you are interested in that tells us, the conditional flow matching loss function is essentially the same as marginalizing the unconditional one is the same as marginalizing the conditional one plus a constant. So there's that.
So the only thing that
Okay. All right. So in summary, for flow matching in practice, right,
Cool.
these are the steps. We define the intermediate variable z. In linear interpolation, the intermediate variable is based on two draws, one from P0 and one from P data.
Mhm.
We define the conditional distribution P of x for everything that we don't have data for in between t time equals 0 and time equal 1. And for linear interpolation, it looks like the linear interpolant between x0 and x1 plus some noise. So this is tied to a conditional velocity field. So we know for linear interpolation, that's x1 minus x0, moving on the joining line between x0 and x1.
Mhm.
We have this equivalence of these for the conical Gaussian pass as well. And then what does it mean to train a model, to train a flow matching model. Now, we can use U conditional to create labels or reference data for a neural network that tries to match these conditional probability velocity fields using a neural network. What do I mean by that? Here. Um, we From this theorem too, we know that if we regress, if we match a neural network to conditional velocities as we also sample points x0. So we sample z, which means that we sample points x0 and x1, and we also sample time between 0 and 1, and we minimize these over and over for different values of x0, x1, and different values of t. This is equivalent, minimizing that is equivalent to minimizing this u of x and t that is unconditional, but we don't have access to it, right? So we know we can show that these two things are equivalent. So by doing this on many, many, many samples, we are hoping to actually achieve that. All right. So that's the process of training. We use these data points, we create reference regression data for the velocity field, and we use a neural network to match that velocity field over and over for different draws of time, x0, and different draws of x1. Now, the last thing that I need to tell you is once you have trained a flow matching model, how do you infer? How do you draw a new sample from it, right? That's the big thing, right? We want to sample from the learned model. Instead of integrating, remember that if we had a model, we had to basically solve x0 and dx dt is u of theta x and t, and we needed to integrate this. Instead of actually integrating it, we can replace it with a numerical integration called Euler's scheme, for example, which takes this now in time steps. In inference, we can do time steps, right? We go from x0 and we say x1 is x0 plus a time step delta t, and then we have our neural network that predicts the velocity at x0 and time equals 0. And we can repeat that to get x2, x3, and this is the general formula. This should not be unfamiliar for you because this is very intuitive. If you know the velocity of a car and you know its initial position, right? The next position can be x2 can be approximated by saying, okay, where did you start from? You started from x1. How long did you move delta t times approximate, u theta is approximate velocity. So velocity is delta x over delta t, right? Do you agree with me that the velocity is delta x over t, which means that you're saying x1 plus delta x should give you x2. So this is an approximate of integrating it. So overall, flow matching, conditional or not, right, is an easier way of training these generative models because we do not have to integrate, right, anything at all. So it's actually easy. Remember CNF's this. We needed to push probabilities as a function in time and then evaluate it to maximize it. But we don't have to do that. We don't have maximum likelihood at all. We only have regression type problems. So it's not a bad thing. It's pretty okay. Now, I want to show you some examples of linear conditional flow matching because it's pretty cool. So, all right, so let's look at this. I'm gonna start with a uniform P0. Look, all of these are uniform, right?
Mm-hmm.
Every point, you can see that the distribution of every point is the same,
Yeah.
right? Now, this problem wants to map samples from this probability to samples from a two Gaussian
Multiple.
probability, right? Very good. Now, let's see what happens. I'm going to move my pointer here. This is x-axis and this is time axis. So I'm going to fix time, right?
Mm-hmm.
At this point, right, what we have done is you can see the blue lines. These are different pairings of x0 and x1. So these are different samples of which variable? What did we call it? Different pairings of x0 and x1.
So what?
These are different samples of z, right?
Oh, yeah.
Right? Pairings. So you can see that for different, we can have different samples going to different, we randomly pick them, right?
Mm-hmm.
Now, we said that the way that we train a neural network is by matching the output of the neural network, which is the velocity, to the conditional velocity coming from the sample. Another way of saying this is the average over different samples and find the average velocity field, right?
Mm-hmm.
Because you remember, as we added more and more samples, right? The picture was becoming more clear, right? So look at the average velocity fields here. So there are these lines, the velocity fields for each one of them is exactly going on that line, which means that the average velocity is going to be somewhere in between the lines. It's that arrow there. Can you see it? The blue arrow? That's basically taking all the slopes and averaging them.
That's a marginal velocity field.
Very good. That's the marginal on this sample, on how many, like 10 or 12 samples, or maybe less, 8 samples, right? So you can see that at this point, the average velocity is actually going straight a little bit down, right?
Yeah.
So if we do this over and over, right, it will basically, the average velocity will tell us, where
We should land.
we should land, right? If I trace it, you'll see that it looks like this. These are the averages, essentially, right? So it'll take samples on this side of this uniform probability and move them towards the top side. And it will take samples of this one and move them to the downside. Can you take a guess why this pass, which is the average?
So actually,
Yes.
it's highly correlated with with how many samples we're gonna choose.
Very good. Very good. Exactly. Yeah.
So it really depends on that. How are we going to say how many samples we want to choose?
It's going to be dependent on that. That's a very good observation. Another observation that is related to this is, I have a question for you. Can you guess why this probability pass, right? Why this U average goes up a little bit and then comes down?
Because it depends on our sample.
Very good, very good.
Yeah.
Some of those samples
Are
went up.
from the top, yeah.
Yeah.
So
Right. Some of them went up.
so I mean we randomly choose our samples, or
Yes. Yeah.
so but how many samples we choose?
It's a hyperparameter. I don't have a good answer to that, but
Oh, but for I mean it's gonna be static at the end of there.
I think so. And the more is better, right?
Because could you go up and down with the I mean not this one,
This one? Okay.
Yeah. At some points we have like more samples. At some points we have less. Am I right? Or
No, you might be right, actually. But remember that time is also randomly chosen, right?
yeah, the time's randomly chosen, but no, I'm talking fix the
Oh,
time
the
and just
pairing.
move. Yeah, just move up and down. So is it random or
Why do we have more samples here, right? Is your question.
no? I
That's a
mean,
good one.
my question is, do we have actually, or is it like
I
the?
actually don't know. I actually don't know.
But I don't think that I see something like this in the code that I mean, it didn't have any like number for the sample, the amount of the pair that we want to.
I agree. I believe the process is, I don't know if they have it. Hopefully they do. Here in the training, you sample time between 0 and 1,
Yeah, yeah.
and then sample Z from the two endpoints, right? So if you're lucky, right, you get many, many, many samples at a specific, so this is time, right? At a specific time, you get many samples. Or if you're unlucky, you don't get that many. So I believe it's not a fixed.
actually, could you go back to the visualization? Could you
Here.
move forward in the like time axis? Yeah. Okay.
I don't know. Can you tell if they're the same number of samples? I can't. I don't know.
No, I'm not talking about the number of
Oh, there is.
samples. Uh,
Oh,
I'm trying to figure out if we move in there, like, could you move forward in like downside of the pic of this
like
picture?
like in X?
No, in time, but in the like the lower level of.
Oh, okay, okay,
Yeah, yeah,
okay. Time is backwards right now.
yeah. Mhm. How it come to this conclusion that it needs to sample from the downside, not upper side at some
Oh,
point.
right here, you're asking how is it not paired with samples from
Yeah,
top,
yeah,
right?
yeah, yeah.
I think it's all
But if
random.
you move it, no, if you move it in the middle side, it's always from both upper and downer side. If you move it in the T, it's always from these two. But if you move it from in top or down, it samples from, yeah. At the beginning, it samples from the down, but at some point it realized
How
that.
about that? It's that one was a basically a conversed one. They have another run. You see the sad face
Hmm.
smiley. That is exactly what you want. It's a very hard one because the samples don't help you here.
Oh, so what what was the difference between these two? I mean, the conditional property part was it different? That's why we get that.
I actually don't know. I think these are like bias. It says good bias and bad bias, right? I think
Hmm.
it's randomly, but they pick the ones that is very
Yeah,
difficult,
yeah.
right? Look, even here, right? The, be, it basically, because half of the samples roughly are going to be from top and half of them are going to be
The bottom.
from the bottom, right? And they need to land somewhere, right? I believe, look, it learns to map the samples, but in a very strange way. So it's not like the top portion of the uniform probability is going to the top part and the bottom portion is going to the bottom. It's not at all like that, right? So it takes different points from different places and maps
Mhm.
that. It definitely luck has a definitely a big, that's the factor. It's a big factor here, definitely. But if you draw many samples, they need to either end up or down, right? So the pass will be learned, but it will be a difficult pass. I will go back to what you were telling me that this pass that it learned goes up a little bit, which is not efficient at all, right? If
Hmm.
you look at this and then these two, the pass that we would draw is very very straightforward, right? But the learned path is not as straightforward just because you got some of the samples that were going up. There is a notion of what's a optimal probability path. We just can't talk about it today, but it's called
Mhm.
optimal transport, OT. You will sometimes see it in the lectures, OT. Um, anyway, what I wanted to tell you then
So
is that
we can also wisely sample from the target and the source distribution.
yes, and what people do is they train this, which is really bad because it goes down and it goes up. They
Mhm.
train this, so now they have a neural network with this U, right?
With- mhm,
And then instead of Z, drawing Z from the linear
mhm,
map, which was t times x0 plus 1 minus t x1,
mhm.
instead of doing that, they draw these according to the not so well working flow matching neural network. So they actually draw samples using this
Yeah,
and use them for training a
yeah.
new flow matching model. So this becomes some good
Worse
sampler.
and worse.
Yeah. I mean, at least, right? It's not sometimes going up and sometimes going down. This is always going down, right? But the path is not optimized. So
Mhm.
people basically use this as initial guess for another flow matching model.
Yeah.
Anyway, let's see a couple more of these and then we should be done. So let's make this to be normally distributed. So, okay, that's fine. What is that? Let me see.
Yeah.
Mini batch optimal transport. So that's what I was telling you that there are ways we should look at mini batch optimal transport, say a bunch of keywords, but all of them are essentially the same thing. Score matching models, denoising,
Mhm.
diffusion models by themselves, flow matching. These are ideas that different people have come up with,
Mhm.
but you see that they are essentially in the same orbit. One theory captures all of them. That's
Mhm.
why I wanted to do this talk for you. Everything is essentially, under the same theory.
Yeah.
All right.